think we're good to go. Thank you for coming.
I'm going to talk to you today about a project that I've started in the last year or two, but which I also think is going to, this type of thinking or this type of work is going to be one of the challenges social science faces in the coming 3, 4, 5, 10 years. It's work exclusively with John Kleinberg. For those of you who don't know him, John is a computer scientist, one of the preeminent computer scientists. He's probably the smart one of the two of us, but I'm the pretty one, so it's better than I'm being taped. This is work that starts with the following observation that lots of people have had. So it'll be trite to start with, so you just have to live with that. That observation is data sets are getting bigger and bigger and bigger in a fundamental way. And as the size of data grows, what does this imply for social science? That is, for how we conduct the business of science. We've known big data has had big impacts in business and in lots of prediction tasks, but I want to understand, what does big data mean for what we do for science? And specifically, I want to think about the following context. You have a scientist who has a hypothesis that they would like to test. And I want to think about how the testing of that hypothesis might change as data gets bigger and bigger. So that's going to be the rules of the game. Scientist starts with a hypothesis and they want to test it. What's going to happen? Now, you might have heard of the scientific method. That is a thing that some of us use. Some people would argue as an economist, well, I don't really use it, but in fact I do. And the heart of the scientific method is what you might call deduction. You start with this hypothesis. It says variable X should matter. You go to your data set and you see if in fact X does matter. If it doesn't, that's a rejection. If it does, that's an acceptance, and we move forward in that way. And what I want to argue today is that that very basic approach changes, and that deduction may not be the best thing to do once data sets get very big. And to do that, I want to, instead of doing science for a bit, I want to do science fiction, which I'm sure, to make another economics joke, is what many of you think economics is. And in this science fiction story, it's going to be set in the 19th century. It's going to be set by a budding medical researcher in the 19th century who is interested in why are people dying in hospitals and wants a biological theory of why people are dying. And somewhat anachronistically, she stumbles first upon a theory, before germ theory, before any of this, of a theory of a mind-body connection. This scientist is convinced that what drives people, what drives mortality, is optimism. That when people are optimistic, they're more likely to survive. When people are pessimistic, they're more likely to die. That's her theory. To test her theory, following a good deductive process, she says, I'm going to turn this optimism theory into a testable hypothesis. What's the hypothesis? Well, if I see my neighbor die, that's got to make me kind of pessimistic. So her hypothesis, her empirical hypothesis from a theory, is that when your neighbor is sick or when your neighbor dies, you're more likely to die. She would like to test that deduced hypothesis. And in fact, she does it well. She finds a hospital where neighbors were randomly assigned. So that's terrific. We have causality. And she goes ahead and says, okay, now let's see what looks in this data. She goes through her data and she finds her theory is accepted. This is terrific. In fact, when neighbors die, the patient themselves is more likely to die. Good news for the optimism theory. Now, of course, hopefully by now you kind of know that it's good news for some other theory, but to this researcher, with her theory, she's kind of accepted it. Now, what would happen? What I want to do now is put a pause on that for a little bit and say, now this is where the science fiction part comes in. Imagine we live in some steampunk world where this researcher actually has access to a very large data set and a computer to use that data set. Okay, even though it's the 19th century. So she's got many, many patients and lots of detail about all the characteristics of the patient, all the characteristics of the treatments, everything that's going on. Could she have done something different? And what could she have done? Okay, that's the question I want to ask in my little steampunk science fiction story. So, to understand what she could have done, I want to just take a little pause here and give you a sense of the way in which I think big data has transformed the world of artificial intelligence and how we can use that insight to transform the world of social science. Some of this may be very familiar to you, so just have to be a little patient with me. And to do that, I want to think about the problem of a classic problem in artificial intelligence, natural language processing. I remember when I was a computer science undergrad, this just felt impossible. Like, people just felt like How on earth are we going to get a computer to understand anything? And to just understand how impossible it is, I want to take in this big world of natural language processing a tiny little problem. And that tiny little problem is called word sense disambiguation. What is word sense disambiguation? It's that, take the word bank. In a sentence, does the word bank refer to riverbank, the financial institutions which seem to get in trouble all the time? Or does it refer to bank left, bank right? It could mean many things. How, in an algorithm, parsing a sentence is to determine what it means. People working in artificial intelligence tried what you and I might naturally try in this situation. Let's say, let's figure out what are the rules that might help disambiguate. So people started writing down the rules, introspecting, thinking about what might work. And, very smart people went at this problem. And they made, I think this is probably not a precise number, but approximately zero progress. This was a problem that just they could not, and this is true of all of natural language processing. And roughly when I left computer science, this felt like this impossible task that maybe in 200 years I will one day have some brilliant insight and we'll crack it. And now I have Siri right here on my phone. What happened? And when you go back and look, what happened was not some brilliant insight deep and sitting in my phone. What happened was big data. What I mean by that is you give an algorithm millions, billions of instances of the word bank, in which you say, in this case, it means riverbank. In this case, it means you just give it tons of learning data. You don't think about exactly what rules it's going to use. You just code up lots of features. Every feature you can imagine. Throw it in there. Just throw it in. And then you have this algorithm learn the associations that predict riverbank. And the more data you give, the wider you make the data set, the better this thing gets towards predictive accuracy. This is like about as, for scientists, it's about as annoying as things can get. You're like, how does this thing work? I don't know, but it works. Isn't that great? And so in some sense, this thing, which is the use of big data, is almost quite different than what we tend to do. We tend to form specific hypotheses in one sense. But what I want to argue is that this thing can be used for this activity. Okay, so now to do that, let's go back to our steampunk world and think of what that medical researcher could have done. She could have done the following thing. She could have said, okay, I've got all of this data, and I've got all these variables. Well, let me go through all the variables and check off the ones that have anything to do with optimism. Okay, roommate health may have something to do with optimism, and let's suppose in this data there's nothing else. But there may be other variables in other data set, like how much was the patient smiling? Oh, well, that has to do with optimism. And so she checks off each of the variables that have something to do with optimism. The rest, she says, I don't know what this stuff is. It has nothing to do with me. Okay, great. Once she's done that, then what would we do? What we would do is we'd say, okay, here's the algorithm. Let it go to work. What it's going to do is come up with the best predictor it can of patient mortality. And we're going to ask the following question. Does it use the variable that you thought was important or not? Now, this is fundamentally distinct in the deductive test. The deductive test is I take the variable I thought was important and ask whether it predicted. This test, which we're calling the inductive test, and I know half the people here know what the word induction means better than I do, so please don't break my heart and tell me this is not induction. The inductive test is, instead of looking whether this variable matters, you say, just figure out all the variables that matter, and is yours one of them? Now, think of what would have happened if she had done this with her particular example of roommate health. She would have said, oh look, roommate health matters by itself, but look at this other variable which seems to be taking up a lot of the action. Did doctor wash hands between patients? I don't know what that is, but look, it's starting to soak up the impact of roommate health. And look, this other variable starts coming in, shared scalpel, and so on and so on and so on. And here's another one that seems to come in. Was the disease tuberculosis, or was the disease buggy accident? Because in this cyberpunk world, they don't have cars yet, they just have buggies. It's a very weird world. So as we go forward, what she'd see is her original variable, roommate health, which she thought was proxying for optimism, is being killed off by these other variables that her theories have nothing to say about, which would make her uncomfortable that she actually had discovered evidence for optimism. She discovered an empirical relationship, roommate health mattered, but remember, theory testing is not empirical relationships, it is testing a theory. And in this case, she would have discovered that actually the data is not confirming her theory as she thought it was. And in fact, if you think of what's happening here, this is almost what the scientific method looks like as it's done by humans, as it unfolds over time and iterations of people by people. She, if absent the computer and all this data, she would have run her one test. Someone else would have come and said, oh, I reran your thing, but I'm noticing this fact. And someone else would have said, I noticed this fact. And slowly over time, someone else would have come up with another theory, which you might want to call, say, the germ theory. And then that theory would have overwhelmed it. But with these large data sets, we have the ability to sort of supercharge that process at least a little bit, where we're no longer doing deductive tests. So that's the heart of it. So the heart of what we're calling the inductive approach, the inductive scientific method, is just like with deduction, starting with the hypothesis you'd like to test. But instead of going and looking just for that hypothesis, letting an algorithm determine what is the best predictor, and then seeing. Now there's a few things to note about induction. The first thing to note in this meeting, the first thing to note is induction is only as powerful as your data set is rich. If you have very few other variables besides your theory, that's... Now, why is that important? That's important because this, I think, is the reason this type of approach was never really practical until the last 10 years. Because we collected data. And data is expensive to collect. What do you go out and collect? The stuff that you think matters. That's why deduction is so powerful. But once you're collecting all sorts of shit, you can edit that out, right? But once you're going to collect all that out, then you will have the ability to look at all these other variables and see what matters, much like in word sense disambiguation. We're no longer defining rules, we're just throwing everything in. Okay. Second, I want you to observe that this is not, absolutely not about causality. The original researcher's mistake wasn't that she misunderstood omitted variable bias. She randomly assigned roommates. It's about the interpretation of causal relationships we discover. It's about, and it can also be about causality, but the core issue is not, I'm telling you about omitted variable bias. I'm trying to tell you about the testing of hypotheses. So that's the approach, and that's what I think has some room to combine this movement in big data with what we tend to do. So let me tell you a practical application of this. We decided to try and test this with one of the old facts in behavioral finance. So behavioral finance is the application of the work Danny and others have done to financial markets. And it's been probably one of, I would say that historically, behavioral finance has been one of the big reasons why behavioral economics really took off. Because in a way, it's like if you're thinking of this like attacking some foreign country, this is not quite the capital of economics, but once you take that territory, then it becomes easy to take everything else because people are like, there's no ways these psychological biases could matter in markets. And, well, they do. And so then you're like, oh, we can take the rest of the ground. One of the early facts in this area was something called the disposition effect, very close to Danny's heart. The disposition effect states that because people are afraid or dislike realizing losses, what we should see is that when somebody holds a stock that they bought at $10, they're much likely to sell if that stock is at $9 than if that stock is at 11, because you just don't want to realize that loss. And it's quite intuitive, and it's kind of an interesting application of loss aversion combined with one other assumption. And in fact, one of the beautiful papers in this literature was Terry O'Dean went and got a very large data set of traders, about 100,000 traders from a brokerage house. And what he showed was, using good deductive science, I took this large data, I looked at stocks, people who were in the gain domain, people who were in the loss domain, and the proportion of gains realized to losses realized was huge. Gains were realized at about 60% higher rate than losses. Very good deductive science. So we thought, well, let's go and just apply inductive science, because hey, this is a large data set with lots of features. And when you go and apply sort of machine learning techniques and you say, okay, let's let the algorithm go through this huge set of variables and pick out variables individually that it thinks are important. This is no longer prediction. This is just if I had to look one by one. In fact, there's good support for the disposition effect. This algorithm is rediscovering loss aversion because it finds this gain variable and says, if I had to use one, this is one of the ones that I would use. It discovers a few others, but it's as if, we're going to put you out of work soon, Danny, it discovers loss aversion, which is kind of interesting. But then if you say to the algorithm, go ahead and use all the variables you could to come up with the best predictor, it doesn't care about the disposition effect. Absolutely uninterested in that effect. The disposition effect much like roommate assignment, appears to have been merely a proxy for some deeper avenue of behavior that really has nothing to do with disposition. Disposition has approximately zero predictive value when you add it. So if you said, here's an algorithm, I hide from it the disposition effect variable. Are you in the gain domain? I even hide from it anything to do with the purchase price. So it can't possibly know anything about the disposition effect. And then here's another algorithm to which I give privilege advantage of my theory, which is purchase price matters. Turns out the two algorithms do exactly as well. There is no benefit in knowing the purchase price. What we thought was the disposition effect appears to be a proxy for something else. Now, it's a little unsatisfying, but lots of rejections are unsatisfying. One thing that's interesting about the induction test is that it's not, unlike deduction, where when we get this doesn't work, we just are told it doesn't work. Induction actually gives us a little bit more. It gives us at least some sense of north, because it tells us these are the variables I used to kill the variable you care about. In this particular case, what killed disposition? Well, two things appear to kill disposition. The algorithm discovers this variable which we could call quartile. What is quartile? Quartile is the price that you have right now, the stock that you're seeing, where does it fall in the distribution of prices over the last 180 days, or that you've seen, for example. If it's in the top quartile, people are much, much more likely to sell than if it's anywhere else. Now you can see how that's somewhat correlated with whether you're in the gain domain, but it has nothing to do with your purchase price, it's just where are you sitting. The other thing that surprisingly seems to matter is if you just look, the last pattern of 3 prices you saw make a big difference. So up, 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 people are very likely to sell. Interestingly, down, 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 people are very likely to sell. So the pattern that really matters if you put it all together is you're in the top quartile and the price goes up, 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 or you're in the top quartile and the price goes down, down, down. That's where a disproportionate amount of the sales happen. Of course, because gain is correlated with being in that space weekly, gain matters, but if you have that variable, which the algorithm discovers, it kills, and it's not just gain no longer matters, is this stuff is much, much more predictive. So just to close it out, that's sort of the application, and I think the things that we're thinking about now are, in some sense, this I think hopefully is a way to combine what I think is the principled elements of science, hypothesis, test, with the sort of almost the data mining, inductive, exploratory, just stuff comes up that is hard to interpret aspect of big data that is now allowed into data sets we have. So that's it. Thank you.
Thank you. Turns out we're going to have a little bit more time. Like we can have 40 minutes for each session. So if you want, we'll have more time for discussion.
Oh, good.
Comments, questions?
I had so
And speak up.
the big data approach. I mean, you're so right about how this is increasingly a method where we're going to reach discovery. But I worry a little bit that, well, for one, we've had data, maybe not big data in the way that we speak of it, for a while. So this approach, it is weird that we talk about the scientific method as first formulating a theory and then generating a hypothesis and then testing it out, because that so often is not how it happens in real life. So you even go back to looking at Tycho Brahe's data, right? So he was a big data guy. All he did was collect data. But then Kepler comes along and finds them and says, hey, there are some rules to this. But it takes Newton to come and actually offer an explanation. And this is what I want to ask you about. Explanation is the heart of the scientific method. And I fear that big data yields better predictions about the future, but we lose sight of getting to the more basic general principles that might actually yield predictions in completely different domains.
I could not agree more with you. So I think maybe I wasn't clear enough. I absolutely am in no way proposing that we use big data to induct up hypotheses and so on and so on. I was still maintaining, I think, the good features of science where wherever your hypothesis came from, that's the starting point. And the goal is very much to use big data to test that hypothesis. Does that Does that make sense?
Yeah.
And so to me, it's
I wasn't saying that you were ignoring that feature. What I really wanted to hear your thoughts on is whether the focus on the success of predictions will possibly make us lose sight of the work that we have to do to try to yield more general explanations. That we might abandon the quest for the more basic because the prediction is so powerful, that we just keep collecting more and more data and saying like, well, I don't care. This is the number. This captures the most variance, so that's what matters.
yeah.
And I feel like we lose some deeper understanding when we're so focused on that. So more, it was just like, do you think that this is actually a danger, or do you think that this is not at all? That we will keep.
I actually, it's a great question. I don't think it's a danger because, and here's why. I think right now the conversation is there, but having worked a lot with these type of techniques now, very quickly, just pragmatically, you run across it. That is to say, there are domains where it's really clear you can just put in your prediction method and just plow forward. But in lots of domains, you very quickly have to get interpretation for exactly the reason that you said, which is we're trying to start with big data, but we're trying to move to somewhere where we don't have as much data. And that's happened so often, but it's like, I think it's just because this is like a new toy that people are sort of it's appealing in this way, but just pragmatic. I don't even think it's going to require anyone to say this. Pragmatically, you just start using it and you're like, oh wait, I can't. And then all of a sudden it breaks. And that's been my experience.
I had a narrower reflection, not on your broader point, although I have some thoughts on that too, on the last issue of prediction about when traders might trade. It reminds me a little bit about the challenge physicians face with prognostication. So it used to be felt, in a way you're talking about, position, velocity, and acceleration of a particle. So when you're trying to predict whether a patient will live or die, initially people put a lot of credence in what was the patient's health status right now. So a patient that, if on a 10-point scale was an 8, would be predicted to live longer, have more prospects for survival than a patient whose position was now 4. But of course it matters a lot. If I told you the patient who's 4 was yesterday a 10, the patient who's, or vice versa, the patient who's 4 was yesterday a 3, and the patient who's an 8 was yesterday a 10, now you might make a different prediction about what's likely to happen. And then of course you could get the third moment as well, not just so you could go downstream. So it's a little, there's an analogy from what you're describing, and eventually you could even imagine that the velocity is much more important than the position, dispense with the position altogether. The other thing that reminded me of what you were describing in that example is the sort of asymmetric loss aversion that physicians have when they make prognoses. So if you imagine that actually a patient's survival, like the classic, real estate, how do you price a piece of real estate, right? The classic Zellner, I think, right? So the real estate agent has to pick a price to sell a house, and you can't publish on the front of the house a density function for what price you would sell it at. You have to pick a single price, and if you pick too high a price, then maybe you run the risk that the house doesn't sell. If you pick too low a price, well, then you run the risk that you left money on the table. So you calibrate and you pick a point, and you have to balance these two losses, not selling versus leaving money on the table. The physician faces a similar problem, which is I have to make a prediction to you of how long you're going to live. You're coming to me for treatment. If I overpredict, then and you die early, then I lose face and I'm embarrassed. And if I underpredict about how long you're going to live, you live great, well then I maybe look fantastic or make treatment decisions otherwise. It turns out that they're very, very, one of the reasons physicians, one of the deep reasons that physicians consistently overestimate survival and are miscalibrated is they feel very differently about selling at $1 loss than they do about selling at $1 gain. So a 1 month overestimate of survival means something very different to them in terms of their loss than a 1 month underestimate. So just two analogies to what you're discussing.
How do these ideas manifest in your work in government?
So
And explain what you do.
Yeah, so I've done various things, and I've done work with the CFPB and work at Treasury. I think this is quite distinct in that, and I think this touches back on the big data, et cetera question. This really is me trying to struggle with the following fundamental issue, which is, can we, and maybe this is not what's going to be the equilibrium in the future, but if we maintain the rigid rule that science is hypothesis test, I'm trying to ask, is there something different about science when data gets very large? And to me, that's interesting because I had always just presumed until I started down this path that when data gets very large, the only thing that changes about science is that we have more power. Great. It's like almost like the focus gets sharper, and that's all. We continue what we're doing, but because it's sharper focus, maybe we can look for smaller effects. But in fact, this stuff has convinced me that it's possible that the qualitative nature of science itself changes. And I know that I'm talking about it in the realm of social science because we understand that, but I suspect the same ideas can be used in other areas, though we're not sure, but in other areas where we also have large data sets and we're testing scientific hypotheses. But
I'm trying to put my finger on what I feel is missing, and from this new approach, and I haven't got it very well figured out, but it reminds me a bit of sort of credit assignment problems in AI and in debugging, and also in connectionism, where you get a connectionist model, train it up, it works. Now the question is why, how, and there are some techniques which can tease out pretty well what's doing the work. I think Sanofsky and Hinton have some, for instance, but I think we need something more here. I guess what worries me is that we'll come to settle for big data prediction and just abandon the search for understanding and say, well, come on, that's an old-fashioned, that's a 19th century idea, a 20th century ideal. Who needs formulae? Who needs understanding when we just push the button and the algorithm gives us the prediction? That is, to me, a depressing prospect.
so that's related to your question as well.
Yeah.
So let me tackle just in a little bit more why I don't think we'll settle there. Is that, and several people have written about this. Donahoe at Stanford has written some very good things about this. There's sort of a misnomer in the word big and big data, and this may be familiar to all of you, but at least let me just talk it through. We could break the word big into two parts: long data and wide data. What do I mean by that? Long data is the number of data points you have. So if you picture the data set as sort of like a matrix or written on a piece of paper, length is the length of that data set. The width is the number of features that you have. Now, these two kinds of big work in exactly the opposite direction. That is, long is really, really good. Wide, it's not that it's bad, but it poses a lot of problems. And why does wide pose a lot of problems? Picture the prediction function work as a search process. The search process is find the combinations of features that work well to predict Y. Now you can see, just a little bit back of the envelope, the combinatorics of it are such that as the data gets even a little bit wider, this thing is growing just exponentially. I mean, just crazy exponentially. So, as a result, when data gets wider and wider and wider, the problem gets harder and harder and harder, and algorithms do worse and worse and worse. As the data gets longer and longer, algorithms do better and better. And so why I'm saying this is because ultimately, as data gets bigger, it's not like it's reducing the need for, let's call it the word curation. What is curation? Curation is the human element of going in and saying, sure, we got lots of these variables, but let's pick these few that matter. Now, and I think this is the part that's missing. And what we're talking about is something interesting is happening in the curation process. Deduction is one end of curation, which is I picked the one feature I thought mattered, and I'm putting that in. With big data, we can put in more than the one feature we thought mattered, but we can't, in many cases, throw it all into the mix. Now, in few cases we can. The data set is sufficiently thin that you can throw it all in, but in most cases you are still left with actually a pretty massive curation problem, and in most machine learning applications, prediction applications, that's all swept under the rug. but the truth is, some domain expert had to curate this thing. Somebody had to decide because there was just way too much. And so there is some interesting and important interaction there, which is also why I think that it's not, I'm not even just saying, notice my comment is a statement about the inherent mathematics of the problem. This is not something where more computing power is going to solve this. It's not something where more data is going to solve this, because this is a double exponential situation where when things get sufficiently wide, we're talking about more data than there are atoms in the universe. This is not, we're not even close to that. So this sort of width problem in blowing things up actually is, I think, at the heart of why fundamentally we have to have explanation. So, and I'm not saying we have an answer to that, but I think that's why there is the need for having a hypothesis, testing, and then continuing to iterate. Does that kind of
No, that's very good. It's like search and chess too. If you had 7,500 first move possibilities.
And it's actually worth, that's actually a great example. It's actually worth noting the difference between search and chess in this example.
Yeah.
In search and chess, my input is not data. It's just computational power to walk down the tree, because the world is given to me.
Yeah.
So the only constraint I have is steps down this tree. In this machine learning world, the length is the limit. I can't just say, get me more data. Well, there are only 6 billion people in the world. I've given you everybody. I can't give you any more. And so that sort of, the length constraint is sort of a very real constraint on the width that we can search through, which is, I think, why I'm quite optimistic that we're not fundamentally just going to somehow miraculously lose the need for explanation. Does that help?
Yeah, well, that's...
Danny?
Oh.
Let me start at the other end. Let's stipulate for a moment that loss aversion is real. I mean, and that people really hate to realize a loss. Now, that would predict some disposition effect. It might not predict the disposition effect. That is, there is a difference. What we have, and I think that's extremely interesting, it might not be the best predictor, but it might still be true. So when you say kill the variable, you might have killed something that in fact is valid and interesting and important. It is just not the best predictor of, when people sell or don't. And we know that can happen. And I'm wondering about that, because then you might actually be losing something through big data. Because there is a consistent story, there is a broad story about loss aversion. And it seems trivial that when somebody has a choice between rewarding themselves by selling something that has gain and punishing themselves by selling at a loss, that they're more likely to reward themselves. If that isn't true, if big data can kill that hypothesis, then we're in real trouble. So here is a hypothesis that somehow must be true. And what you have shown is that it's not the best predictor of people's choices of.
Yeah.
And because it is not the best predictor, it's not an independent predictor. You have come up, with a conclusion, which is a strong conclusion. We've killed that variable. I'm not sure you have killed it. I'm not sure you should kill it. That's the question I'm raising.
I think there are two ways in which we could be wrong in saying we've killed the variable. One is, we focus narrowly on stock sales, and that's the only thing in the world, and we're trying to figure out, did we say something meaningful about the disposition effect there? The second way is, look, we don't just care about stock sales, and this harkens back to what we've been saying. We care about a variety of things. And even if this variable is not the most important predictive variable here, it's possible that it's the third most important predictive variable, but across many, many, many domains. And so, as a result, it's a foolish thing. So I think these are two separate elements of it. And let me take them in part. The second one, I think, is the easiest to sort of talk about, which is that I think what I find valuable in the inductive test at some level is it's worth just comparing it to the deductive test. In that sense, induction, I think, will lead to many more of these instances where variables look unimportant or far less important in this context. But I think that's something social science has to sort of come up with, which is that our theories are not meant to, or can never be, so good that in every context they do very, very well. So we have to be amassing evidence across a variety of contexts. And so I would completely agree. If you said to me, we are going to go and get data on housing, do I believe that this fact that disposition is less important here or unimportant here, given the other variables, does that mean disposition wouldn't be important here? I don't know. And so I think of this as having supercharged one part of the process, but by no means have in any way supercharged the other part, which is important for social science, which is to look context by context and start to understand. And I totally would believe a world where we found it, disposition was third most important or second, or was important if we didn't know, but because the quantile is not something you can look at in other places, etc. So that, I'm agreeing, though in this case I will say that it gave me a moment pause, because when we look at the variable that matters, in this case the quantile and the price distribution, price dynamics, that made me feel like, actually, now that I go to the housing world, I would also be curious about those variables. So that gives me guidance, but kill is too strong a word for the second one. I completely agree with that. It's more saying we've learned a signal that this thing wasn't independent.
Yeah, then I have a small technical question. I assume that you did it the way I would have done it, but the disposition effect, as I understand it, is that you take an individual who has a choice, that is, he has a portfolio, there are some winners and some losers in the portfolio, and the question is, which is he more likely to sell? So is that the way it was set up, or because in general, that is, if you don't set it up as a sales problem, if you just predict what as a choice problem between selling a loser and selling a winner, if you just predict selling, you could get something entirely different.
No,
and
that's right.
conversion would be completely irrelevant.
That's exactly right. No, it's very much set up as you're given this string, here's a person, and you're given this string of everything that's happened to them, as well as their purchase price, and so therefore you can say, okay, for this person in this stock, here's everything you know about them, and now you'd like to make a prediction about, is that person going to be selling or losing? And just so you get a sense, that person, that type of string, there are many such strings, and so there will be ones where that person will be in the loss domain on another stock, that person, and so that's the signal that I think the Odin paper correctly got at, because it collapsed all those strings down and said all the times that you're in gain versus all the times in loss, and then that's what. But I don't know if that's what you mean,
No,
or
I mean, my question was whether you restricted your analysis and your prediction to cases in which the portfolio included a winner and a loser. Because if you didn't, then your results get a completely different interpretation. The disposition effect is about a choice.
right.
And the story you were telling us is about a prediction. And you could have a portfolio that is all winners or all losers. And if you allow those portfolios inside your analysis, you could get your result, and that
I
would
see.
even bear.
Got it. Yeah.
So more
So
particularly, I mean, does the outcome of other stocks held by the same trader affect the likelihood of selling or buying the index stock? I think, right, across stocks, not
Yes.
across individuals.
Yeah,
So are you comparing individuals who are at a gain, they're more likely to sell than individual versus within the individual?
that's right. That makes total sense. We've done a little bit of stuff, but maybe not as much as you'd like, but we've done a little bit of stuff on the entire portfolio. Is the entire portfolio in a gain? Where is the stock relative to the other stocks in the gain? And those never get off the ground, which I take as a sort of a mental accounting thing, that each things are being individually accounted for. But we haven't done, and we can do this, it's a great idea, is just literally compare this person and say, here are two stocks that the person themselves holds at this time, which one is more likely to be sold. That's a thought experiment we can easily
I
do.
mean, that's interesting because of something it tells you about big data and the analysis. That is, that when you construct it in the deductive way, when you construct a story about the disposition effect, you really very clearly have a choice in mind.
But to be fair, the Odin experiment wasn't the one you had either.
No.
No. So then was
I
the
mean-
deduction. When we did deduction with Odin, we also did just take all winners and compare to all losers. So in some sense, I I take your comment, but I don't think that's about. I think that's almost a slippage, a mental slippage we all have had around what is the prediction, and maybe this is nice because it's really forcing us to sharpen exactly what the prediction is. That's exactly right.
Samuel,
Oh,
thank you.
thank you.
Good.